Hello everyone, welcome to Tuteetute. In this video we will see the important questions related to analog circuits, and this particular video is related to GENCO 2023 preparation. First question is about operational amplifier. So in operational amplifier, the effect of the asymmetries between the internal circuits driven by inputs can be reduced by. So here what they are telling is effect of the asymmetries between the internal circuits. So in the operational amplifier, internal circuit will be there, okay, and because of the, we can't able to take, for example, differential amplifier is there, we can't able to take two exact similar transistors, so some slight changes will be there in the saturated voltage or in the saturation currents, like that. So because of that slight change, we may get output without applying the input. Okay, this is what we need to understand here. So generally, if input is 0, output must be equal to 0. But because of this asymmetries, what will happen means, even though input is 0, output will not be equal to 0. This is the problem we are getting. Okay, so we need to adjust this output to 0 whenever input is equal to 0. So how it is possible means, if you see the options, adding resistor at the input to VCC side, driven by an AC voltage source, connecting a Zener diode at the input side, connecting the slider of the potentiometer to VCC minus. So which is exactly suitable here in order to make this output is equal to 0. Whenever input is equal to 0 means we need to adjust the voltage. Okay, so anyhow here AC input voltage is 0. This input is equal to 0 is nothing but we are talking about the AC input only. But in order to working function of the that particular operational amplifier or the differential amplifier which is available in the operational amplifier, DC supply is there. So by adjusting the DC supply, we can make this particular output voltage is equal to 0. That means how it is possible? Certain potentiometer is required. Okay, so here option D is the correct option. So connecting the slider of the potentiometer to VCC minus, we can able to, that means VCC, okay, or VCC minus, whatever it may be, we can able to adjust the voltage. Okay. Next question is, by considering the standard notations in approximate analysis of the voltage divider biasing configuration, which of the following conditions should be satisfied? Okay, so the question is related to voltage dividing biasing circuit. Okay, which of the following conditions should be satisfied? Okay, we will study about the voltage dividing biasing circuit, and in order to get the stability of the circuit, generally biasing circuit is for what purpose? We need to make the Q point is stable. Okay, so our criteria must be like that. So in order to achieve that one, we will get some base current. Okay, in the analysis of that particular voltage dividing biasing circuit, if you observe, input side we have to apply KVL and we need to get IB, that means base current. Then we will get IC. Okay, IC is equal to beta IB, like that we will get, and by the application of the KVL in the output loop, you will get VCE. So VCE comma IC, that is a Q point. So in that particular process, we need to work for the stability criteria. While doing that one, you may get some condition that is related to this particular question. Okay, so here I am taking first the voltage dividing biasing circuit. So voltage dividing biasing circuit involves two resistors at the base side, R1, R2, and here VCC is there, and we can connect this emitter to emitter resistor RE and collector to collector resistor RC. This is the general voltage dividing biasing circuit. Okay, so for this particular part, we can apply the Thevenin's rule. Okay, so we can able to make the series connection of one voltage source and one resistor. So I'm applying that one. So it is equivalent to the transistor as it is I am taking with RE and RC, and here VCC I have provided. Then here one resistor and one supply, like this I have taken. Okay, and this is VB, and since it is connected to base, I am taking RB. So what is RB and VB? This is actually, so since base current is very less, you can able to take these two resistors are in series. So the voltage at this particular point is the voltage across R2 only. So VCC into R2 by R1 plus R2 according to voltage division rule in between the two resistors, that is VB. Next, if you make this is 0 and if you send the output current this side, these two resistors will be in parallel. So R1 is in parallel with R2, that is RB I am taking. So VB is equal to VCC into R2 by R1 plus R2. This is a Thevenin voltage, and the Thevenin resistance RB is equal to R1 is in parallel with R2. So that I got this particular circuit. Okay. So now into the base IB current is flowing, and through the emitter we will get IE current, that is equal to IC plus IB, and IC is equal to beta IB, and if you take IB is common, here 1 plus beta is there. So 1 plus beta into IB current flowing through the RE resistor, IB current is flowing through the RB resistor, and here base to emitter you have emitter to base voltage. So in the input loop we can able to write now KVL. So if you write KVL in input loop, so what you will get, you see. So supply voltage is VB, that is equal to IB RB, that is the voltage drop across RB, and from across the this particular base emitter junction we have voltage is VBE, and the voltage across RE is RE multiplied with IE. So what we will get here, IB into 1 plus beta into RE. So we are looking for actually IB current. So IB is equal to VB minus VBE by RB plus 1 plus beta into RE. Like this we'll get. Okay. So actually we need to have the collector current because it is one of the coordinate of the quiescent point. So IC is equal to beta IB. Okay. So see carefully here, IB into VBE minus VB minus VBE by RB plus 1 plus beta into RE. So in order to make this particular IC independent of the transistor, even though you are replacing the transistor, the IC value should not be changed. Okay. For that purpose, what we need to do? We need to make it independent of beta. So if you see this particular equation, here beta must be cancelled by this beta. Then only we can say IC is independent of transistor or beta. That means I should have this 1 plus beta times of RE should be very much larger than RB. Then RB can be neglected. This RB should be neglected. Okay. That means what we need to take the condition 1 plus beta into RE is greater than RB. Like this we have to take. Beta is very large, so we can neglect this one also. So beta into RE must be greater than RB. So in general, greater than means 10 times greater we have to take. That means it is equal to beta into RE must be equal to 10 times of RB, or you can take greater than or equal to 10 times of RB. Like that we can able to take. So if you see the options here, beta into RE. So everywhere beta into RE is there. Here beta by 2 RE, beta RE, here beta into 2 times of RE, here beta RE is there, which is greater than or equal to 10 times of RB. RB means here what? R2 only. That because here, okay, in the options they have given this R2 with respect to R2 they have given, but in general RB is nothing but approximately R2 only, because you see here RB is equal to R1 parallel with R2 I have taken, and we got the condition with respect to RB, but this can be approximately equated to R2 only because of the less value of R2 compared to R1. So you can replace here RB with R2, then option C is the correct option, or this is also condition you can able to take. That is the thing. Okay. So you should be familiar with the derivations also. Okay. In that particular derivations, what is the conditions we are getting, that is what you need to remember. Okay. Now the next question is, by considering standard notations, the time period of a linear ramp generator in IC555 timer is. Okay. So IC555 actually can be used as a stable multivibrator. It is a timer actually. So we can able to utilize IC555 as a stable multivibrator, monostable multivibrator, like that we can able to utilize. But here they are asking to generate the ramp signal. Okay, and while generating that one, the time period, what is the time period of that ramp generated, that is what we need. So in order to establish this one, so what we need, that ramp is for certain amount of time duration only, na? That means this particular time duration we can able to achieve by keeping the IC555 in monostable multivibrator, because in monostable multivibrator, okay, stable state is there and quasi-stable state is there. This particular amount of time we need to make as quasi-stable state amount of time. If you give the trigger, then it will enter into quasi-stable state and stay for t0 seconds, and automatically it will come for stable state. When you give the one more trigger, again one more ramp signal will be generated. How we will get this particular ramp? In the sense, this ramp linearly it is increasing. But actually if you see the monostable multivibrator operation, the capacitor charges exponentially. How to make that particular capacitor charge linearly? That means in the ramp wise, without having the exponential manner, is nothing but, if you see capacitor equation, V is equal to 1 by C integral I dt. How we can get here ramp voltage? We can get ramp voltage by making this particular current is constant. So I by C is constant, integral dt means we'll get here T. So it is like alpha into T only, na? So we are going to get the voltage is ramp voltage. So how it is possible means we need to make a current flowing through the capacitor must be constant. If you can able to make that one, then this is possible to get the ramp from the monostable multivibrator operation of the IC555. Okay, so you need to use the IC555 as the monostable multivibrator. In that you need to make a current flowing through the capacitor must be constant. Then ramp voltage will be established. Okay, then we'll take like this. Whatever the current is flowing through this particular capacitor, that current must be equal to what we can able to tell dq by dt. Like this we can able to take dq by dt. Okay, so we can take here dq is equal to I dt. Like this we can able to take. Okay, and this particular current is constant anyhow. Current is constant, and how much time it should be available here? How much time it should be available means, that is we are representing with t0, na? So we are representing with t0, and this particular charge must be equal to, it is related to capacitor. So Q is equal to CV. So capacitor is V and voltage. How much amount of voltage will be taken by the capacitor during this particular t0 time? Okay, during the t0 seconds, how much amount of voltage will be charged by the capacitor? If you see the internal structure of the IC555, you will be having two comparators. Okay, lower comparator, upper comparator. One of the terminal of the upper comparator is connected to the capacitor, and where another terminal is connected to 2 by 3 times of VCC. Why we are getting like that? If you see the voltage dividing circuit of the IC555, we have like this. This is VCC. Here 3 resistors of same value will be available. So here how much voltage is there means 2 by 3 VCC only, na? For example, resistor R is available. So you need voltage across the 2R. Total resistance is 3R. That's why 2 by 3 VCC. So the voltage will be taken by the capacitor by the time T0 is 2 times of VCC by 3. This is what we need. Okay. So from this you need to get this T0 value. So T0 is equal to 2 times of VCC by 3 into C. This is the capacitance value by I0. So by I. Okay. So this is the basic equation we got now. Now you please check the options. This is not complete solution actually, but you try to check the answers. 2 by 3 VCC into C. Okay, 2 by 3 is missing here. 2 by 3 VCC into C. So there is a chance for getting the C is the right option. And here 2 by 3 VCC is not there. 2 by 3 VCC into C. So for D also we have the chance. Now further we have to perform. So how it is possible to get this I value? Okay. How to get this particular current which is flowing through the capacitor using this monostable multivibrator operation of the this IC555, that is what we need to Fine. For that particular purpose, you take one amplifier. I am taking this one. You take it is VCC, this is RE, and here how much voltage is there? VE, and from here to here VEB voltage will be there. This is R1, R2. Okay, so we can write here VCC is equal to, this is the current. We require this current only. Okay, so VCC is equal to I into RE plus VE. Okay, plus VE, but that VE can be written, VE is actually this node voltage. Okay, it is involving this VEB and this VB also, so that VE I am writing as VEB plus this VB. Okay, this VB can be written as, according to voltage division, this particular concept, VCC into R2 by R1 plus R2. Now I think you can get some idea related to this one. Okay, get I value from this one. I is equal to something you will get, and substitute that I value here. Then you will get complete T0 value. Okay, 2 by 3 VCC into C, and here whatever the I value we are getting, if you substitute here, you will get option C is the correct option. That is what you need to understand. Okay, so very simple only na. Here what is I RE will get, first I am writing this one. So it is equal to, send all these terms this side. So VCC minus VEB minus VCC into R2 by R1 plus R2. This is what we are going to do. That is what I have told. So it is equal to, if you multiply with this one, VCC into R1, VCC into R2, here minus VCC into R2 is there, both will be cancelled. So VEB into R1 plus R2 by what will get, R1 plus R2. Okay, send this RE this side also and inverse this one. Okay, because here we need 1 by RE. So if you inverse this one, R1 R2 into R1 plus R2 into RE, you see here it is available. Okay, and remaining part you can able to see in the denominator. So option C is the correct option. So you need to know here 2-3 things are there. One is you need to know about the IC555. Okay, you need to know about this ramp generator, how we can able to get ramp generator using the capacitor action means. So through the capacitor you need to send constant current, that is one point. And about IC555, what you should know, okay, what you should know in the sense that particular quasi-stable state that will be available for how much amount of time? T0. But by reaching that particular T0, how much amount of voltage will be charged by the capacitor means 2 by 3 VCC into 3. Okay, you can able to understand this one if you know this IC555 operation. Okay, that is what you need to understand. So here 2-3 concepts they have mixed and framing the question. Now we'll see the next question. A 100 kilovolts amps 50 edges single phase transformer has a ratio of secondary to primary turns as 0.1. Okay, so 0.1 turns ratio, that means N2 by N1 is equal to 0.1, that is equal to 1 by 10. The secondary voltage at no load condition is 100 volts. 100 volts, that means V2 they have given 100 volts. What is the value of the primary voltage? That means V1. So it is straightforward question only. They have given turns ratio, that is N2 by N1, and they have given secondary voltage, we have to calculate the primary voltage. So there is a relation between the turns ratio and ratio of the secondary voltage and primary voltage, that is N2 by N1 is equal to V2 by V1. V2 by V1. So N2 by N1 is 1 by 10, that is equal to V2 is 100 by V1 is like this. Okay, so that by cross multiplying we will get V1 is equal to 1000 volts. Okay, so option C is the correct option. Now the next question is, by considering standard notations in VCO, the center frequency. So VCO means what? Voltage controlled oscillator. Voltage controlled oscillator. So what is the meaning of this one? It is producing some oscillations. The oscillations are containing the frequency, but it is voltage controlled. Whatever the frequency is there, that can be controlled by voltage. Okay, so voltage controls frequency. Voltage controls frequency. Okay, that means if you take the equation of F naught, that should involve voltage. Okay, but if you see the options, all are frequency equations, all are containing voltages only. So you can check here. Okay, V plus V, VC, like this we have. But actually if you see the VCO diagram, where you will be having the supply voltage that may be indicated with V plus, and you will be having the control voltage also. Okay, so we need the difference between these two. Okay, and it will control the frequency. But in option C and option D we have a difference only. Okay, but which is exact one is nothing but if you see the operation of that one, you can remember this particular value, that is 2 times of V plus minus VC by V plus R1 C1. That is the equation you need to follow. Okay, you try to remember that particular equation. Next, if square wave is impressed upon either a point contact or PN junction germanium diode, a resistance does not change instantaneously from its forward value to its back value, or vice versa. Which one of the following is required for this change to take place? Okay, they have taken one PN junction diode, for example. This is the barrier, P-type, N-type. Okay, so square wave is impressed upon this one. Okay, the resistance does not change instantaneously from forward to its back value. That means, for example, it is in forward bias. Actually here you have given not DC supply, you have given one square wave. Okay, so when you give the square wave, how much time this particular high voltage is there, during that particular time it is in forward bias only. Okay, T is equal to T1, suddenly what is happening to the square wave means its value is changed. So it is in forward bias now, but here immediately what will happen? Here you will not get reverse bias immediately. This is the applied voltage. Okay, but here forward bias means some amount of voltage will be there or some amount of current is there. For example, we will talk for the current. Current is flowing like this. Okay, but immediately when you apply this one, the strength of the current will not become 0. It will be reversed. For example, here 2 milliamps is there. Here minus 2 milliamps will be there. Strength is same amount only. Magnitude if you see, that is 2 milliamps only. Okay, immediately 0 current. Reverse bias means approximately 0 current we should get. That will not happening instantly. So, but you have provided this particular change in the applied voltage at T is equal to T1. At T is equal to T1, just polarity is reversed, but strength is same. Okay, after that it will maintain for certain time also. Then slowly it will be reaching to 0. Okay, this is called storage time. It is called transition time. The combination of these two is called reverse recovery time. So based upon this particular reverse recovery time only, whatever the supply voltage we have made instantly, due to this one we will not get instantly this 0 current in the diode. It will take certain amount of time, that is called recovery time. So based on that only this is happening. Okay, this is the recovery time. Next one. The voltage gain of CE amplifier circuit may be approximated for an ideal input AC source and is given by. So CE amplifier. So you take any CE amplifier, for example basic low frequency analysis CE amplifier if you take. What do you know about the CE amplifier means? We can tell that it can be working as the voltage amplifier, it can be working as current amplifier, and it provides 180 degrees phase shift in between input voltage and output voltage. All these things we can able to tell. And if you take one circuit, this is RC, this is VCC, and here for example load resistor RL is there. And if you draw the low frequency analysis of this one, what will happen? DC source we have to make 0. So here RL resistor will be there. This RC will coming in parallel with RL. That means effective load resistance is the parallel connection of these two. That means RC is in parallel with the RL, we have to take into account. And output is measuring across this one. So this particular effective resistance will be coming in the numerator of the voltage gain only. That is what you need to remember. And the CE amplifier provides a 180 degrees phase shift. That means its gain should be negative. Okay. So that is what we need to understand. So see the options here. Gain is negative means option B is there, option C is there. But as I said, output we are taking across RC parallel with RL. So that should be in the numerator. So option C is the correct option. Okay, easily we can able to identify that one. Next question we'll see, that is advantage of using a class B push-pull transistor amplifier over class A push-pull transistor amplifier. So easily we can able to tell in class A, the operating point will be there in the middle of the active region. Okay, so because of this one, the advantage is faithful amplification you will get. Okay, but in case of class B, 2 transistors you will use and each transistor will be either in the cutoff region or in the saturation region. So it may be here or it may be here. So what will be there means only one half cycle only you will get. So the total power dissipation is almost 0. Okay, almost 0. So the power dissipation is 0. That is what we can able to tell as the advantage of the class B push-pull amplifier compared to our class A amplifier. So if you see the options, negligible power loss at no input signal. Okay, this is okay. Okay, that is what we can able to tell. Now the next question is, the longest wavelength that can be observed by the silicon which has the band gap of 1.12 electron volts is 1.1 micrometer. So they have given energy and wavelength. The longest wavelength that can be observed by another material is 0.87 micrometer. Then the band gap of, okay, they have given this band gap versus wavelength. So energy is equal to HF. Okay, this is the equation we can able to take for having the relation between energy and frequency. But they have given with respect to wavelength. So we know that lambda is equal to C by F. So we can rewrite this particular equation. Energy is equal to H into frequency means what we can write here? C by lambda. Okay. So we need here H is Planck's constant and C is light velocity. Both are constants only. So that we can tell here energy is proportional, or that particular energy band gap is inversely proportional to wavelength. Because we are dealing with two energies, I can take the formula like this: E1 by E2 is equal to lambda 2 by lambda 1. So E1 I am taking as 1.12, that is what they have given, by E2 we have to calculate, that is equal to lambda 2 is 0.87 micrometer by, this is 1.1 micro. Micro I am not writing, anyway those will be cancelled. So what I need here? E2. E2 is equal, by cross multiplying this one, 1.12 into 1.1 by 0.87. Okay, so result will be in electron volts because energy. Okay, so option will be, if you make this calculation, what you will get means numerator is higher, denominator is lower, so surely you will get greater than 1, but 3 options are there like that, and this is nearly equal to 1.5 only, so you will get option A. Now the next question is, a single phase full wave rectifier uses semiconductor diodes. Okay, full wave rectifier uses the semiconductor diodes. The transformer voltage is 35 volts RMS. So RMS voltage is nothing but Vm by root 2 we have to take, that is 35. So from this we can write Vm is equal to 35 root 2 volts. So we have here Vm, peak voltage we have. The load consists of capacitor value is 40 microfarad. Capacitor value is 40 microfarad and load resistance is RL is equal to 250 ohms. The diode and transformer resistances and leakage resistances are neglected. If the power line frequency is 50 Hz, DC current in the circuit. So we have to calculate IDC. So IDC is equal to how much? This is what we need to calculate. Okay. So what is the procedure here we have to apply? Because here we used a capacitor filter. Okay, this is the full wave rectifier output. Capacitor filter is nothing but the capacitor charges, discharges, it will be like this. But if you take one charging and discharging, it will be for half of the time period only. Okay, that is what we need to consider into the account. So this is Vm. This AC input will be available for V gamma. This is the variation. So from this, VDC is equal to, we can write peak voltage minus V gamma by 2. Okay, from this we can able to write this one. And this VDC is equal to output DC voltage is nothing but DC current into low resistance value. Like this we can write. Now, according to the concept, how much charge is charged by this particular capacitor is equal to discharging charge. Okay, this is what we can able to take. This is for charging, this is for discharging. Okay, and here we can able to utilize for IDC into how much time it will be charged means T0 by 2. Okay, time period is T0, but it will be charged for half of the time. So it is equal to Q discharge. This is capacitor into V gamma. That is what we can able to take. The variation is V gamma. So from this, because here we need V gamma value, we need to replace this V gamma. So I am writing for V gamma is equal to IDC by 2 into C. Here T0 is there, that one I am writing as 1 by F0. So this value try to remember for the full wave rectifier. For the half wave rectifier it will be IDC by F0 into C. But for the full wave rectifier it is IDC by 2 F0 into C. So substitute this one here. Then Vm minus, here by 2 is there, already 2 is there. So that IDC by 4 F0 into C is equal to IDC into RL. So now Vm is equal to, send this term this side and take IDC is common, so that you will get RL plus C by 4 F0 into C. From this you can get IDC. So Vm by RL plus C by 4 F0 into C. Okay, this is what we can able to utilize. So here all the values we have, Vm value we know, RL value we know, capacitor value and frequency value, all the values we know. So if you substitute, you will get IDC is equal to 132. Okay, 132 milliamps will get. Like this we have to do the solution. So here you need to know the concept of full wave rectifier with capacitor filter and how these equations are written. If you have the command on that one, you can able to do the proper solution. Okay. Next we will see another question, that is the overall decibel dB voltage gain of the multi-stage amplifier is. So for example, you have two stages. First stage voltage gain is AV1, second stage is AV2, and the total cascaded connection of these two can be taken like a single multi-stage amplifier having the voltage gain is AV. And the relation among all these things is AV is equal to AV1 into AV2. So this is given like this. Now you convert into dBs. So when you convert into dBs, 10 logarithm we have to take now. So 10 logarithm of AV is equal to 10 logarithm of AV1 into AV2. So it is equal to 10 logarithm of AV1 plus 10 logarithm of AV2. So now AV in dB is equal to, whenever 10 logarithm is there, you can write dB. So AV dB is equal to AV1 dB plus AV2 dB. That means addition we have to do. So the gain in dB of the multi-stage amplifier is sum of the dB voltage gains. So option C is the correct option. Next question. The band gap of germanium at room temperature is. So for silicon it will be more, but for the germanium it will be less, that is 0.7. You need to remember this one. Okay. For silicon also you try to remember. In a differential amplifier, there are two sets of input signals. In the first set, V1 is equal to 50 microvolts, V2 is equal to minus 50 microvolts. In the second set, V1 is equal to 1050 microvolts and V2 is equal to 950 microvolts. The common mode rejection ratio CMRR is equal to 100. Percentage difference in the output for the two sets of the input signals will be. Percentage difference in the output voltage we have to calculate. Okay. Generally, the basic output voltage can be given due to two parts. One is due to differential gain, second one is due to common mode gain. Differential mode gain, when you have here, it has to be multiplied with differential voltage. Common mode gain means you have to take here common mode input voltage. This is one thing. Next, if you don't have this part, only you have to calculate using differential mode gain like this. Okay, because both are there, we can represent with 1 and 2 like this, V01, V02. What they are asking is V02 minus V01 by V02. This is what they are asking. Okay, difference, percentage difference they are asking. So that we have to take like this and multiply it by 100 also. Okay, that one we can do later. So if you subtract these two, minus or plus whatever it may be, AC1, that means by subtract these two will be cancelled. So by AD into VD, like this will get. Okay, but actually CMRR is nothing but common mode gain will be in the denominator and differential mode gain will be in the numerator. Okay, so here we reverse we have, that means this part is 1 by 100. It is equal to 1 by 100. What is common mode input here? Common mode input means you add these two and divide with 2. So what will get? 2000 by 2 means it is 1000, and differential mode gain means by subtracting these two will get what will get? 100. Like this will get. Okay, so how much you will get here? 1 by 10, that means 10% you will get. This is what they have asked. So option A is the correct option. Next one. In an operational amplifier having a specified signal bandwidth of 1 megahertz and the closed loop gain is 200 millivolts per millivolts, 200 volts per millivolts, cutoff frequency FC. Generally, when we take unit gain bandwidth, it is the ratio of bandwidth and gain. Okay, like this we can able to take. This bandwidth, it will become this cutoff frequency only. Cutoff frequency value can be taken as the bandwidth. Like this we can take. And they are asking us to calculate the cutoff frequency only. So unity gain bandwidth by gain. So it is equal to what they have given. Gain is 200 volts per millivolts. By sending this milli to the numerator, it will become 10 power 3. And whatever the bandwidth they have given, that is what I am taking. That means it is 1000, 1 mega. What is that one? 1 mega by this is into 10 power 3 by 200. Like these two will be cancelled, and here answer is 5. So 5 is the answer. Like this we can calculate. Okay. Next one. If the bias current in IC741 operational amplifier is IQ is equal to 19 microamps, okay, IQ is equal to 19 microamps, and the internal frequency compensation capacitor C1 is equal to 30 picofarad. What is slew rate? Okay, slew rate means what? Slew rate of the operational amplifier. That is nothing but what is the rate of change of voltage? That is what we need to take. So slew rate is nothing but how fast the output voltage will be changed, dou by dou t, dou v by dou t. Okay, voltage variation with respect to time. That is what we need to get. Okay, so but it is related to capacitor. We know that I is equal to C into dV by dt. Na? So here only we have the slew rate. Okay, so dV by dt is equal to I by C. That means they have given IQ. Okay, IQ by C1. IQ is 19 micro by C1 is 30 pico. So answer is there in microseconds. Okay, volts per microseconds. So this part is okay. So it is equal 19 by 30, 0.190 is there. So 3 6 is 18. So 0.6 like that we will get. So option D is the correct option. Okay. Next question we will see, which one of the following statements regarding the slew rate is correct? So it is like definition of the slew rate only. Just now I have told you, it signifies how rapidly the output of the operational amplifier can change in response to the changes in the frequency of the input signal. This is what we can able to tell. Okay. Next, which one of the following is correct for an ideal operational amplifier? For ideal operational amplifier, input resistance is infinity, output resistance is 0, and bandwidth is infinity. CMRR is infinity. Open loop gain is infinity. These are the characteristics you need to remember for the ideal operational amplifier. So if you check the options, option C is the correct option. RA infinity, R0 0, bandwidth infinity. Okay. So thank you. With this we have completed some important questions in the analog circuits. Okay. In the preparation for this TS GENCO 2023. So based upon this particular lecture, you can able to justify your preparation. Okay. And you can able to improve your preparation and you can study well, and all the best for your future. Thank you.